forget that you can still request extensions for any late assignments in WebAssign. You can do that up to 2 weeks after the assignments are due, and they were due on the 8th, so you still have time to to request those extensions. And I described how to request the extensions in an email I sent out a couple days ago. All right, so this is 2.1 continued, just moving through our discussion of functions. We were talking about domains and ranges of functions, and we talked about, well, we really spent most of our time on Monday talking about the definition of a function and how a function must take and take each input and send it to an output, and not have one input going to two separate outputs, right? So I think we talked about that enough last time. I said it about 5 different ways. So let's just pick up right where we left off, talking about domains of these two functions. Functions that have an x in the denominator, and functions that have an x under a radical. Also, the whole discussion about range, we'll talk about that range a little bit more in later sections. I believe it's section 2. I forget which one it is. 2.5 is when we start talking about that. Maybe 2.6. Okay, so what are the domains of these functions? We'll recall that the domains of a function, or the domain of a function, is the set of input values denoted by x, right, that are allowed to be plugged into the function. So for f of x here, for f of x, its domain is going to be all real numbers, right? All real numbers except for one in particular. It's going to be every single real number except for that one particular number that's going to go here and here, and we're going to connect these two intervals with a union. So I went in detail about where this is coming from, this setup, this kind of interval setup with the union there. I went into detail about that last time. But kind of the point is, for this particular function, f of x equals x minus 1, the value that cannot be plugged in is 1, right? Because that will yield a 0 in the denominator. So the number 1 is the number that's not allowed. So in general, if you have a function with a variable in the denominator, you're going to take that denominator. So you're going to take the denominator and set it equal to 0. So for this particular one, I would say x minus 1 equals 0. And solve for x, so x is 1. This is the number, there we go. This is the number that x is not allowed to be, right? That's what we're doing when we set the denominator equal to 0. We're trying to find that value that it cannot be. That's the number that goes here and here. So just as another real fast example, like if I had h of x is equal to 1 over 2x plus 3. Right, so what is this function's domain? So when you look at f of x up here, it's kind of easy to tell that 1 is not allowed, right? Because 1 minus 1 is 0. That's, you don't really need to do this to figure that out. But for this one, maybe it's not so easy to tell what the number is. So if I want to find its domain, I'm going to set that denominator equal to 0 to discover what x cannot be. I'm going to have 2x is equal to negative 3, subtracting 3 from both sides. And then x is equal to negative 3 halves. that's the value that's not allowed for h of x. So if I wanted to write its domain, I would say this, here's the setup for a function like this that has an x in the denominator. This is going to be the setup, where this empty spot is that number that's not allowed in the function. So I would put -3/2 right there. So that would be for h of x. So that's the process for finding the domain of a function that has x in the denominator. So let's talk a little bit more about this g of x thing. G of x, so equal to, well, just in case you can't see it anymore, so there it is, square root of x minus 1. We discovered that the domain for a function that has x under a square root is kind of easier to write down because it's just like an entire section of the number line, right? There's not a hole in the number line like the like this one has a hole in the number line at one particular value. But square roots are different. They don't allow for negatives at all. So whenever you've got a square root of an x, you're getting rid of like an entire chunk of the number line. And what number is cut off here? Well, it's that one value again, but we allow 1 to be plugged in. So that's a 1. We allow 1 to be plugged in because 1 minus 1 is 0. Having a square root of 0 is okay because it's not in the denominator. So that's okay. And then we say off to infinity because you can plug in any bigger number you want. The point is you can't plug anything in that's smaller than 1, like for instance, like a 0, because then you would get 0 minus 1 being a negative. So how do I discover this number? So for the rule up here for the function with an x in the denominator is to take that denominator and set it equal to 0 and you solve. That tells you where the hole in the domain is. For these functions with a square root, you take technically the stuff under the radical is called a radicand, but I'm just going to say take the stuff. We don't need fancy terms. I mean, not at this point, really. Take the stuff out from under the radical. And what do we want to say about it? What needs to happen in order for this to be a legitimate domain? Like, what needs to happen? We need it to be not negative, right? We need it to be not negative. So we're going to say take the stuff out from under the radical and set it greater than or equal to 0. Greater than or equal to 0. So what does that look like as a mathematical statement? It's going to be x minus 1 greater than or equal to 0. This is what we want. We want the radicand, the stuff under the radical to be positive, including 0. 0 is okay. That gives me x must be bigger than or equal to 1. And then I have to know that that corresponds to this interval. And how do I know that? Well, I kind of went over that last time, but I'll just draw it again real quick. You know, so if this is 1, if that's the number 1, then x being greater than or equal to 1 includes 1, and it's all those numbers over there, which is exactly what this interval, because infinity is that way, negative infinity is that way. It's exactly what this interval says here. So those are the rules for functions with a x in the denominator, finding the domains, rather, of functions with x in the denominator and finding the domain of functions with x under a square root. Okay. Okay, so I'm about to be out of paper. Let's see where we are. Let's just do a practice one real quick, and I'm gonna call this, I don't remember what example we're on, so I'm just gonna call this a practice problem. find the domain of, we'll say f of x equals square root of 2x plus 1. And I will give you guys a second, and then I'll call on one of you guys to answer that. Okay, so I'll go from what I'm seeing is the bottom right and work my way left. So Taylor, what do you think would be the domain for this function?
The domain, let's see.
So look at the rules that I have for functions under a square root. You take the stuff happening under the radical and set it greater than or equal to 0, and then you solve for x. So our first step would be 2x plus 1 greater than or equal to 0. And then how would I solve for x from here?
You would take the 2 and the 1 away, right?
Yeah, so subtract the 1 from both sides, right? So we're trying to solve for x, so I need to get rid of the...
Okay, you're talking for x first. I thought you were taking the... See, like, how you took the things from under the radical right there?
Yeah.
Okay, well, so you do -1 on both sides to cancel out the 1.
Yep.
And then you do 2x. I mean, yeah, divide 2x on both sides.
You divide by 2, right?
Yeah, 2. My bad.
And there we go.
Yeah.
Good. So once you get there, then you say we have to be able to transform that. Sorry, there we go. Transform this little inequality into an interval, because that's how we write domains. We use intervals, not, well, you can say it this way, but for pretty much all you guys are going to need to also be comfortable with the interval notation too, especially if you're going on to... When I say pretty much all, what I mean is we're going to do it in this class, and also you're going to do it in trigonometry too if you take that class. So from here, if x is greater than or equal to -1/2, since it says or equal to, that's why I'm using a bracket to say that I'm including that value. And all the numbers bigger than that are just going to go off to infinity. There we go. So there's one of those. So are they always... So I know, when you're in math class and you're trying to understand things, you're going to look for shortcuts, right? So you might be thinking, okay, it's just always going to be like this bracket and then an infinity, and whatever the number I get here, I just put it there. It's not necessarily always true, because you could have something negative under here. In fact, I'll just show you one real quick. Let's take another function, g of x equals square root of 1 minus 2x. No, wait. Yes, that's what I want, 1 minus 2x. Okay, so I would say I'm going to set that thing greater than or equal to 0. Now you've got to be good with algebra here, or arithmetic, or I guess it is technically algebra. So we're going to subtract 1 from both sides. We're solving for x, so we're going to subtract 1 from both sides because the 1 is positive. So we're getting -2x. That negative is attached to the 2 there, so -2x greater than or equal to -1. And now I'm going to divide both sides by -2. But recall that when you divide in an inequality problem, when you divide by a negative, you have to flip the inequality around. And when I say the inequality, I mean the little symbol. So we're flipping the inequality symbol around. And by the way, what is -1 divided by -2? Well, that's just going to be 1/2. So what is my domain going to look like here? Well, this says x has to be less than 1/2. X has to be less than 1/2. So this is going to flip my interval over. So my domain here is not going to look like this form. It's going to be flipped around, where the bracket is now on the right side and the negative infinity is happening on the left. And just to help you understand that, I can draw a picture here of what's going on with this inequality. So I'll just put 1/2 here. Here's 1/2. I've got 1/2 included, right? X is less than or equal to 1/2, so that's why it's a closed dot. That's why it's a bracket here. And I want all the numbers less than 1/2. That's all of these off to negative infinity. So it's best to, what's my point here? It's best that if you don't know how to get from inequality to interval, draw a picture of the number line. And then this should help you get from picture to interval. Okay. Now let's go on to something a bit more straightforward, which is evaluating functions. Let me get paper. I go through so much paper. Probably go through like 1/2 pound of paper per day. That's okay though. All right. So, well, first of all, are there any questions about this domain stuff? Because you may not have, oh, why is my camera not focusing? Hello. There we go. You may not have ever seen this like interval notation, or if you have, you might have forgotten it or whatever. So is everyone good, or do you feel like you need another example? Okay. Okay. All right. So let's go to evaluating functions, which is a bit more fun. We're going to talk about evaluating functions at numbers. Basically, this is what you would call plugging in numbers. Evaluating functions at numbers and, though, at other functions. What does that mean? That means we're going to be plugging functions into functions, which sounds scary, but it's not too bad. All right, so let's just start off with an example. I didn't write down what example I left off with. I'm just going to start if you have your notes and, on Monday or whatever day, Wednesday, we left off at example 3, then you can call this one 4. I don't remember which one we left off on. So I'm just going to start my enumeration over. Example 1. Okay, so we're going to let f of x be x squared minus 2. A. Evaluate the value of f at x equals -1. Okay, so what does that solution look like? Well, when they say f at -1, or rather f at x equals -1, we write our little f for function. And then in the little window that tells us what we're about to plug into the function, instead of an arbitrary x, which is kind of like just a placeholder for any number we want, instead of that, we plug in the specific number. So f at -1, and then we say is equal to, and then we write this function, except the x gets replaced by a -1 wrapped in parentheses. So we'll say -1 squared, and the parentheses are just there to make sure that our order of operations doesn't get messed up. Okay. So you would not want to just write -1 squared without parentheses, because you might miss the step where the negative is going to end up going away on the -1 because it's being squared. Okay, so then we still need to evaluate this, right? All I've done is plug it in, but I actually need to compute it. -1 squared is just 1, and then -2. And then that's going to be -1. Okay. So what am I saying? F at -1 is equal to negative. It's coincidence that it ended up being the same value. We'll do another one to show you that it can definitely be all sorts of different values. Okay, let's try evaluate. I could have just said find the value, whatever. It's a little redundant. The value of f at, let's just say x equals 4. Whoops. I was trying to minimize. There we go. Okay, evaluate the value. Okay, same function. So f at the input 4 is going to be equal to parentheses 4 squared minus 2. So hopefully you're saying like you would really just call this plugging in, right? Just plugging in. I mean, really, like if you had to explain to someone what we're doing in layman's terms, that's what you would say, just plugging in. Okay, 4 squared is 16. And 16 minus 2 is 12. No, not 12. 14. 14. Here we go. So that means this point, f of 4 equals 14, satisfies this function. When you plug in 4, you get an output of 14. Here's something I noticed they asked in the homework. The net change in the value of f between x equals -1 and x equals 4 is so when they're asking for net change in the value of f, they're asking for net change means like if you subtract them, what is the overall change? And they're asking for the net change in the output values. So that means I'm going to say the net change would be f of 4 minus, f of 4 minus f of -1. That's the net change. This is exactly what this says in words. Net change in the value of f between -1 and 4. Okay. And since this x value is bigger, it's coming first. And by the way, we can actually evaluate this because we have f of 4 being 14, right, from up here from part B, and then minus f of -1 was itself -1, so there we go. So 14 minus -1 is going to be 15. That's just a little extra part in one of the homework problems that I saw that, net change, I guess it's a good little thing to point out. We won't do a whole lot with it. I just wanted to make sure I did one explicitly so that when you come across that problem in the WebAssign, you're not like, what is going on? I want to add one more part to this and say evaluate the value of f at, I did -1 for, how about x equals a? Okay, So my input is A, so it's going to be f at A is equal to, and then x squared minus 2 is the function, but I'm replacing x with A, so I'm going to have A squared minus 2, which, by the way, since A is not negative or any, well, I don't really know what it is. I can just go ahead and drop those parentheses. So it really just, it's literally like I changed the letter of the function, right? Okay. So you can do that. You can plug in other letters into functions. We're going to plug entire functions into other functions. And let's call that example 2. So let's move to a new function and a new example. And let me see what kind of functions they give. Yep. Let's say g of x is equal to 3x squared plus 7. Okay, we're going to evaluate, I'm going to shorthand this, g of x plus 1. Okay, so this time I am taking this function, and instead of plugging in an x, I'm plugging in an entire x plus 1. So let's see, who's next in my list? Okay. Kimberly, what do you think the right-hand side of this would look like?
Wouldn't you just like put in that equation with the other equation, like next to each other? And
Not
you
mean like multiplied next to each other?
Yeah.
It wouldn't be like that. It would be exactly this. So I would start with a 3, but what is x getting replaced by?
The x plus 1.
Right, so instead of x squared, what will it be?
It'll be the equation x plus 1.
Yeah, that squared, and then plus the 7. Okay, thank you. Oh, and by the way, it's not x plus 1 is not an equation. It's I know what you meant. It's just a little function. It itself, x plus 1 is just a function in here. So what we're doing here is we're plugging a function into another function. So what is this actually? Well, okay, before I evaluate it, let's just talk a little bit more about this. Literally, this x got replaced by x plus 1 wrapped in parentheses. It has to be wrapped in parentheses, right? Everything else is the same. 3 plus 7, everything else is the same. Cool. So now our job is to actually like expand this and compute it. Recall that the x plus 1 squared thing, you don't just distribute the square. You say x plus 1 all squared is going to be, why am I taking this off on the side? Well, because it's going to be the most amount of work that we have to do in evaluating this. So x plus 1 all squared means this whole thing times itself. So we got to, distribute the x, and so we're getting x squared plus another x, and then moving to the 1 and distributing it. 1 times x is x, and then 1 times 1 is 1. So we're getting x squared plus 2x plus 1. Okay, just doing that off on the side. So now I'm coming back over here and saying 3 and then parentheses, this whole thing, this x plus 1 all squared turns into this, x squared plus 2x plus 1. Still wrapped in parentheses because I still got to deal with that 3. And then don't forget the 7. Okay, now I'm going to distribute the 3. So 3x squared plus 6x plus 3, and then don't forget the 7. Finally, do I see any like terms? Yes, I do. Those two constant terms. Okay. That's it. That would be the answer for evaluating g of x plus 1. There it is. Okay. Oh my gosh, sorry, my phone is going. Let me throw it over there. Okay. So any questions about that one? Are we feeling okay? I'll do more. But I want to get you guys, I want to get your feeling for this, like where I might be losing you, if you're getting lost. Any comments about this one or questions?
Could we do
I'm
another
not like really
example?
lost on it, but I am a little confused. Like if you could do like another one.
Yes, yes. And yeah, so I will. And Aviana, what were you gonna say?
Oh, I was just going to ask if we could do another example.
Okay, cool. All right, so I will, but first I want to do a second part. So this example 2 is dealing with this function. I want to do a part B to this, just to make a point, and then we will do another example with a different function. Okay, so part B here is going to be slightly different. I want to evaluate g of x plus g of 1. So you might see why I'm doing this. I'm comparing. After we do this, I'm going to compare this thing to this thing because they look the same, right? It's just the plus sign is out. We're adding the two functions here, and here the plus sign is inside, right? So let's just quickly do this one. This one will be easier because g of x is just 3x squared plus 7. So let me write this, hang on. Okay, g of x, so that's literally just writing the function down. That's that part. And then there's the plus sign. Now, what is g of 1, by the way? Maybe I should do that off on the side. That's evaluating this function at the number 1. So g of 1 is equal to 3 times 1 squared plus 7. 3 times order of operations, right? 1 squared is 1. And then multiply by the 3. And then 3 plus 7 is 10. Okay, so that's what g of 1 is equal to 10. So that gets tacked on right here. So this ends up being 3x squared plus 17. That's 7 plus 10 is 17. Not the same, right? That's the only point I wanted to make here. That and why am I making this point? Well, because a lot of students I've seen in the past will see this and think that it means to do this, but it doesn't. They're not the same. They're just different problems. Now, you may be wondering, like, but they look so similar, surely there's something more to say. And the answer is yes, for certain kinds of special functions, this would be the same, but in general, it won't be. So whenever I'm asking you to compute something like this is the route to go. Now, with that being said, let's do another one like that for practice. So I'll call it example 3. And, you know, what's really tricky about this, I feel like, is that the functions have squared stuff in them, right? So I'm going to pick another one like that. Let's say 2x squared minus. In fact, let's make it a little bit more involved. There we go. Put another term in there with an x in it. And I'll just make this one part. Let's evaluate f of x minus 2. So this one's going to be a bit more involved. These are kind of some of those questions that they're not particularly hard in the math, right? But it's kind of testing your organization, right? Your organization skills. Like, you could probably write all the pieces down, but then keeping track of them, putting them back together, not getting lost in your own work, you know, that's kind of, it's testing. Oh crap, am I recording this? Yes, okay, okay. It's kind of testing your ability to keep track of your work as you go. These kind of problems are. So, first of all, just getting it written down, f of x minus 2 is going to look like, so I'm going to replace every x with x minus 2 wrapped in parentheses. So there's going to be that number 2 coming down. And this x turns into x minus 2 and it's squared. So that's this term. And then minus 6 times x minus 2 in parentheses. So there's that term with the x being replaced by, so every single x gets replaced by x minus 2. And then don't forget the 5 hanging out at the back by itself. There we go. Now, right here, I suggest taking anything like this that's being squared, taking it off on the side, to figure out what that's going to be. So x minus 2 all squared is the same as, first thing you want to do is write it out, expand it. Don't be tempted into taking a shortcut where you just square both terms, because that's not correct. We're going to say x times both of these, so that the first one is x squared, and then x times negative 2 is negative 2x. I didn't give myself enough room here. There's going to be another negative 2x, and then finally negative 2 times negative 2 is positive 4. And that's giving me x squared minus 4x plus 4. So is everyone good with this in blue here? Let me know right now if you're not, because we can do practice with this, and it's really critical, honestly. Like, if this is going to be one of those really critical things, techniques that we're just going to keep using, you know, over and over again. Honestly, it's going to keep coming up. So is everyone good with this, or should I can do another one in like green down here, kind of like an unrelated little tangent problem?
Could you do another one?
Yes. So let me just say, so we'll come back to this. This thing is going to get plugged in here, but we'll come back to that. So just a little tangent right here. Let's say x plus 6 all squared. Hang on. Did my light just turn on? Okay. So that's x plus 6 all squared. Tell you what, I feel like that's too small. We'll come back to this example 3. So this is a side problem. X plus 6 all squared. There we go. First thing you need to do is recognize that a square, well, rather that number 2 up there, which we call square, right? When something is squared, that means you take this entire thing, whatever's being squared, and you multiply it times itself. You multiply it times itself. Okay, so that's the first step. The second step is to say, when you've got two things multiplied by two things, the technique is to take the first, now you may just call it the FOIL method. I never like calling it that, because that idea of FOIL method doesn't work for anything bigger than a 2 by 2 case. If you've got like two terms times 3 terms, or 3 times 3, then that idea doesn't work. So what I like to say is, take the first term and multiply it by both of the terms in the other set over here. So that x times x is yielding x squared. X times x yielding x squared. Then this x, still with this x, times positive 6. X times positive 6 yields a plus 6x. Okay, now I move on to the second term, which is that positive 6, and I'm going to send it to both of these. Positive 6 times x yields another positive 6x. And then the last term, positive 6 times positive 6, yields a positive 36. Whenever you're squaring something like this, the two central terms are going to end up looking exactly the same, and they're going to double each other. Right, just like back here when I had two negative 2x's and they doubled to become a negative 4x, same thing's going to happen here. My two 6x's are going to double to become a 12x. They don't cancel each other out, right? They double down. If they're both negative, they become more negative. If they're both positive, they become a more bigger positive. So anyways, this is the answer for this particular problem, for this little side problem. 6x plus 6x being 12x. Okay, so over here we had the minus signs going on, but still those two central middle terms, they're both negative, so when you combine them, they double. They don't cancel each other, right? They double, leaving you with a negative 4x. And by the way, where does that, so this is where I'm coming back to like organization. Where the heck does this go over here? Well, this is supposed to be this thing, right? So I'm going to have, no, I'm going to go ahead and get rid of this now. I'm going to have 2 times all of that, x squared minus 4x plus 4. Okay, that's that whole thing all done. And then minus 6 times, I'm just going to copy the rest of that. I'm not going to do any more steps at once. So there we go. All right, now I'm going to go ahead and distribute the 2 here. So 2x squared minus 8x plus 8, that's me distributing the 2 to all 3 of these terms. And so I'll do my distribution in one step. So that means I'll go ahead and distribute this minus 6. Negative 6 times x gives me negative 6x. Negative 6 times negative 2 is positive 12. Okay. And Nikita, I'm forgetting something. What's the last thing I need to do for this step? Or Devin, what's the last thing I'm forgetting for this step?
Combine like terms.
Not yet, not yet. That'll be my next. That's going to be what I do in my last step. But before, I'm not done writing this stuff.
Are you going to subtract 8?
Nope, not yet. Not combining like terms yet. Anyone see what I'm missing?
The plus, is it the plus 5?
Yes, that's it. That's it. So it's this again, this is one of these problems where you get so wrapped up doing some, this kind of stuff and doing all your distribution. It's super easy to forget to bring down that constant thing hanging out at the back, right? So one thing that I do is I like to, you see how I got my equations all lined up? I like to line things up, keep them so things are kind of stacked roughly so that I can tell where they're coming from. And that helps me to, as I glance up at my previous step, I go, oh, the plus 5, can't forget that. Now I'm going to combine like terms. So now I need to be real careful about combining like terms and be careful with like what's negative and what's not, right? So here I've got a negative 8x. The negative is attached to the left. That's the negative 8x and a negative 6x. So I'm going to say that those combined, they're both negative, so they should become more negative. And in fact, they'll become negative 14x because negative 8 minus 6 is negative 14. And then I've got a bunch of constant terms to combine. I've got a positive 8, I've got a positive 12, and I've got a positive 5, which is going to be 8 plus 12 is 20 plus 5 is 25. That's the answer for. So the final answer, f of x minus 2 is equal to 2x squared minus 14x plus 25. There we go. So remember, I'm not, just in case you're getting a little confused about like what the final answer should look like. I'm not solving an equation, right? I'm not like trying to solve for a x or anything, right? I'm just taking a function, a given function, and plugging something into it, which means at the end, I should have some function, some new function involving x's and other numbers. And does it often look kind of similar? Because it kind of looks the same as f of x. It should look roughly the same, you shouldn't like get like a weird square root function just from plugging in, something like this into a function like that. Anyways, don't worry about that. The point is you should end up with a new function like this. Okay, let me glance at the homework and see if they give you anything more heavy duty than that. They do. That's good. I'm glad I looked. I actually forgot about this kind. Let's say that we have example 4. Let's say we have a function f of x equals 6x squared plus 3. Part A, we're going to find f of a. That'll be easy enough. Part B, we're going to find f of a plus h. And then part C, we're going to put it all together into this crazy looking thing that you won't see again until much later in math, if you're even going to take more math. But this equation is actually super important in math later on, in calculus. But it's also just kind of a good exercise for pre-calculus students. Okay, so part A, solutions in red over here. F of a, it's literally just rewriting the equation, or no, the function with the letter A instead of X. That's not really much else to say there. Okay. So that's the answer for part A, 6a squared plus 3. Part B is not quite as easy because we've got, a whole new thing being plugged into the function. So we're going to say 6 times, instead of x squared, it's this whole thing, a plus h squared, and then don't forget the plus 3 at the back. For the sake of time, I'm going to jump some steps because I do want to try to get done with 2.1 today. So the steps in between here I will leave to you, but you will end up with a squared plus 2ah plus h squared, and then plus 3. So it's your job to later go back through your notes and figure out how I got from a plus h all squared to this thing. A squared plus 2ah plus h squared. And as long as you expand them out, you'll see where that came from. Okay, now I'm going to distribute the 6. 6a squared, 6 times 2, 12ah, and then plus 6h squared. And then barely room for the 3 there. There it is. Okay, so that's part B done, because there's no like terms here. That's a squared, that's ah, that's h squared, and that's a constant. These are all completely different like terms. I'll read it out loud just in case you can't make that out too well. That's 6a squared plus 12ah plus 6h squared plus 3. Now, part C, putting it all together. This is again an exercise in organization. You're going to have a giant fraction bar, and you can go and put that h down there. That's just an h, not a function thing. It's just literally the letter h in the bottom. Now first comes f of a plus h, so that's this whole thing. 6a squared plus 12ah plus 6h squared plus 3. Literally this whole thing right there. Then the minus sign. And I'm going to subtract f of a. So since I'm subtracting it, I need to make sure I wrap it in parentheses, so I subtract the entire thing. So there's f of a. So just to reiterate here that this is f of a plus h from right there. And this is f of a from up here. And it's wrapped in parentheses so that I remember to subtract both of the numbers. The entire f of a is getting subtracted. Okay, so now I'm going to come to some new paper so I have room to really write this big. I have 6a squared plus 12ah plus 6h squared plus 3. Distributing the negative here, minus 6a squared minus 3. See why they both became negative? Because of this minus sign. That's what I've got. They're both supposed to change signs because I'm subtracting this entire thing. That's why I made sure to wrap them in parentheses here. Now I combine like terms. I've got, and you'll see that your like terms are going to cancel very nicely here. This positive 6a squared and negative 6a squared, positive 3 and negative 3. Nice. Okay, so now I have 12AH plus 6H squared all over H. Those are the only two pieces left because 4 of them canceled out. Now notice that I can factor an H out of both of these on top. So factor an H out of both, like a greatest common factor. By the way, I could pull a 6 out too, but let's not bother with that. I can pull an H out of both. If I pull the H off of 12AH, then I'm left with 12A. If I pull an H off of 6H squared, I'm just left with a single H. And then finally, notice these two H's will cancel. That's why I factored an extra H off, because I knew it would cancel in the bottom with that one. So I'm finally left with 12A plus 6H. That is a long problem, but it is a great exercise in not only your ability to evaluate functions at other functions, at other numbers and stuff, but also your ability to put it all together, right? To put it all together. Okay. So last thing for 2.1. Now I know that was a lot, but I don't have time to do another one of these. It would take too long because I want to talk about the last thing in 2.1. But remember, you can always go back and rewatch this this particular problem. Okay. Last thing is to describe a function verbally or in words. Let's just take h of x is equal to 2x plus 4 versus g of x equals 2 times x plus 3. So if we're going to describe what these do in words, we have to describe what's happening to x. We have to describe what's happening to x and we have to be very aware of our order of operations. So for h of x, we would say, what happens to x? In order, we multiply by 2 and then add 4, right? If you were describing what happens to x, like if you plug in x equals 1, you would multiply it by 2 and then add the 4. G of x, on the other hand, order of operations is a bit different here because of the parentheses. We add 3 and then multiply by 3. No, sorry, by 2, by 2. Add the 3 and then multiply by 2. That's it for, let's not get too crazy with describing, I could write some really wacky functions and describing them in words could become like really involved, but let's just kind of leave it at that. All right, so these last few minutes I want to talk about 2.1. We're going to be looking at graphs of functions. So next time, you might want to bring some graph paper if you like to have clean, neat graphs. Also, you should go investigate, become familiar with this website because I'll be using it. It's called Desmos, DESMOS.com, and then /calculator. It's a really useful graphing calculator online, and I'll be using that. So you should just know it exists, maybe go check it out, maybe play with it a little bit, because we will be talking about actually graphing functions in the next section. And I'll have homework problems to mark for review for you for 2.1 next time on Monday, I guess. All right.